Okay, now it's my very great pleasure to welcome Noah Kraitzman, who's going to be telling us about brine inclusions in first year sea ice, which follows on very nicely from Ken's talk just now. Thank you.
Okay. Hi, everyone, and thank you for coming. I told Cecilia before that I moved to work on sea ice after I met Ken. And I think after his talk, it's very clear, right? We should invite people who are not doing sea ice to listen to your talk, and everyone will want to join. So thank you so much. So I thank you for introducing me. So I'm going to talk about brine inclusions in first year sea ice, and this is a joint work with Keith Promislaw, who was a genius in dynamical systems from Michigan State University, and Brian Wattel, who loves Stefan problems. So if you have any Stefan problem, you should go to him. He's at the University of British Columbia. I'm going to give a very short introduction because we all know everything about sea ice at this point. I'll derive the model that we have for the evolution of brine inclusions, and at the end, we'll analyze it a little bit. So when I talk about brine inclusions, we can look at ice cores that are dug out, and we can zoom in. And if we zoom really far, we can see the brine inclusion. These are these salty liquid regions within the ice. So what happens during the freezing process is that we freeze the seawater. The solid ice doesn't like the salt, so it rejects it. The freezing process is much faster than the diffusion of salt. So the salt is being captured within this process, and we get these regions of high salinity that don't freeze. These brine inclusions are very important part of the microstructures of sea ice. Ken talked a little bit about the rule of 5. So once the temperature is warm enough, above -5 degrees Celsius, these brine inclusions connect to form meter-long channels through which fluid can flow. And this fluid flow is important for the transport of heat, nutrients, and carbon throughout the sea ice. Brine inclusions are important for albedo. The size and their distribution within the ice might change the albedo of the sea ice. And of course, brine inclusions are very important for our ecosystem. In particular, if we look at the sea ice, we can find regions of algae and microbes that live inside these brine inclusions and brine channels. When categorizing sea ice, we consider the age, depth, and temperature at which they were harvested. What we usually get from measuring sea ice, we look at the temperature, the bulk salinity, and the brine volume fraction. And that's a lot of information. So let's focus on one. So the top row is 2013. And the bottom row are measurements from 2014. And these are real measurements. And what we see here is the temperature. And it's very clear that the temperature is a function of depth. However, what's a bit more interesting is if we look at the temperature gradient. The temperature gradient seems to be spatially uniform throughout the ice core. Maybe not at the bottom where it's all completely mushy layer, but definitely at the top. The rest of the information, we have the bulk salinity and the brine volume fraction. And these graphs are, well, they have a lot of information and they're too complicated for me to understand them. So what we said is, okay, thinking again on the freezing process, assuming that there's no salt within the ice, which is a very close to accurate assumption, we can take the brine volume, the bulk salinity, and divide it by the brine volume fraction. And then we get this awesome graph, this awesome linear data that now I can more easily understand. So that's the salinity within the brine inclusion as a function of temperature. And it sits nicely linearly on the cryoscopic line. So the cryoscopic effect, definitely those who came from the US, you know that when it snows, you throw salt on the sidewalk, right? We have these bins of salt at the University of Utah. And the idea is that once you add salt to water, you reduce the freezing temperature. And that's exactly what we have here. And it turns out that this cryoscopic effect is linear for small deviation in temperature and for low concentration of salinity. So here, theta star, that's the freezing point of pure water. And this side, that's the cryoscopic effect. I'm motivated by experiments. Excuse me. So this is an experiment done by Light and her group. And what they did, they took sea ice with brine inclusions, with these 4 brine inclusions. So that's where they start. It was frozen at minus 13 degrees, and they wanted to look at the heating and cooling cycles. So what they did is they heat it up, minus 8, minus 4. It's really hot, almost like here in Adelaide. No, not a good joke. I'll change it for next time. And then they cool it back down. So what do we see? So the brine inclusions, when you warm up the sample, they increase and they merge. Right here, we have a small, tiny one that merged with a bigger one, and then all 3 merge into one tube. Then they freeze it back again. So the tube contracts, right? It doesn't break again. Why? Don't we want to freeze it back again and get something similar to the original one? So the question is, what went wrong when we refreeze it when they? So one of the problems with lab experiments is that they are done without temperature gradient. And without temperature gradient, you're getting different type of freezing. So we were motivated by this image. And then we said, okay, we have our model, let's check. We have no temperature gradient. We took a tube with brine. So the outer dashed line, that's how it started. And we put it in the refrigerator. So the left side, that's our mathematical model. And that's the experiments I just showed you. And just to be super clear about that, this is a real experiment done in a real lab with real ice. And this is a real mathematical model done with real pen and real paper. Why are you laughing? I can show you the pen. No, I want to make sure that when I say I'm freezing my model, I'm just freezing it on the paper. I don't have refrigerators. So I took my brine tube and I freeze it. It contracts exactly like happened to theirs. And that's it. It stopped. So we can say, oh, it works. However, since in my mathematical refrigerator, I can add temperature gradient. So that's what I'm going to do. So now I took the exact same brine tube, only I'm looking at large temperature gradient, which is like we saw from the measurement from the Arctic. And sorry, I'm changing the temperature. And this corresponds to going from June to March. And I'm not taking the time backwards, but I'll assume I'll go to next year's March. And I'm looking at the top of the ice. So these are the conditions, let's say within 30 centimeters of the ice. So my nice brine tube contract it very fast, pinch off in the middle. So our mathematical model breaks down once we get to this pinch-off point. I don't know what happens after. I can only assume. However, we do assume that this tube will pinch off in several points and will create a chain of equal sizes inclusions. We can also take large temperature gradient, but look deeper into the ice. Let's go 80 centimeters deep and see what happens there. So the temperature are warmer now. And what we see is that I'm starting at the exact same tube. It will start contracting, and then it will pinch off at the top. What I expect to see in this case is a chain of very small inclusions with a few big inclusions at the bottom. Okay. So I showed you my results, and then you can say, okay, so I'm done. You can stop listening to me at this point, but I will show you how we got there, and I'll derive our beautiful model. So what I'm modeling here, and we saw CI. CI is enormous, right? We can talk about different length scales and everything. What I want you to imagine is that I'm holding a box of sea ice with one brine inclusions inside, and now I'm going to freeze it or thaw it, and I'm looking at that. So you imagine this big box, and how big is my box? It's like microns, right? It's like microns big, but go with me and let's imagine my box. So I have a three-dimensional domain. I'm going to have the phase parameter, which is 0 when it's ice, and it's 1 when it's water. I'm going to have the temperature, the salt. I want to include my cryoscopic effect, right? We saw that this one plays an important role. Okay. To describe a physical phenomena, we need the energy of the system, or in this case, we're going to use the entropy of the system. So in 1990, Penrose and Five introduced several models to describe the internal energy and the entropy of temperature-dependent phase change. Now, we're going to do what we can. We're going to choose the simplest model that they offered. So in the simplest model, the entropy density, the entropy is a spatial integral of an entropy density of this form. Okay, so here the entropy density is a function of the phase parameter, its gradient, and the temperature. Now, the last two terms, so we have this W naught. W naught is a equal depth double potential, and we have grad phi squared, which penalizes surface area. I'm going to use this first term and modify it because we want to include the cryoscopic effect in our system. So this is our modified entropy. The first term is the thermal entropy, which comes out to be natural log of n, which is relatively simple. We have the penalizing term and the double well. I'll talk about the double well in a second, but they're both scaled now with age. So age is a very large parameter, and that's the ratio of inclusion length to interface. And this W, so before we had W naught, which was equal depth potential. And now I'm going to take a tilted double well potential. And the reason I'm going to do that is because this tilt, I want to depend on the cryoscopic effect. So I want to say if psi, that's my cryoscopic term, is positive, my system is going to prefer water. And if psi is negative, well, I'm going to prefer ice. So we have these terms. The last term that we have in our system is this R. That's the salt entropy relative to liquid water density. So again, to understand the idea of what I'm doing with this parameter, let's think about the freezing process. So remember, I have this cube of ice, one brine inclusion inside, and I'm freezing it. So what happens is that inside the water solvate the salt ions. And during the freezing process, unfavorably, we're actually reducing the entropy. Okay, you can think about it as if the water are magnetized to the salt ions. And I actually need to put work into ripping them apart. Okay, so that's what basically happens. We push them away from the water, we get regions with very high salinity, and then because of the cryoscopic effect, it's not going to freeze. Okay, so that's my entropy, or my entropy density. And now we want to derive our system, and we want our system to be thermodynamically consistent. So to satisfy three conditions, we want conservation of internal energy. We want the entropy to increase throughout the system, throughout the domain. And of course, we want to conserve salt. Okay, so our system, or our entropy, as it's defined now, it's using the phase parameter, the temperature, and the salt. I can use the phase parameter, I can use the salt, I want to conserve salt. I cannot use the temperature. The temperature is a terrible parameter to work with. Basically, because other than telling you what you need to wear in the morning, temperature has no use. Ah, you got it, good. So the temperature has no use. We do not conserve temperature in our system. Okay, so the main idea of temperature is that it satisfies this fundamental thermodynamic relation, and we want to change variables. Basically, I want to leave the temperature and move to some internal energy, which I can work with. So that's what we're going to do next, or not next in this slide. I'm skipping the gory details, but basically we have this thermodynamic framework which relates the entropy density to the internal energy, and we get this internal energy. Now, I have so many letters on my slide. I don't want you to read the letters. I want you to understand what they mean. So here, when we look at the energy, and the internal energy, what's interesting about it is that the first term, this one, it looks very similar to some kind of an antiderivative of the cryoscopic effect, which is awesome because I wanted that in my model. And then the last two terms, well, they relate to the thermal entropy. So they come from there. So now we're going to change. Basically, I'm eliminating temperature from my system. Now everything will be as energy, salt, and phase parameter. And that's good because I can work with that. And let's derive the system. So the curvature flow of the system is determined by the gradient of S. S is the entropy. So we have our entropy. We have phi, which is the phase parameter, and that's going to give us the dissipation mechanism because we do not conserve water by itself and ice by itself. We can get a gradient flow. We have two conservation laws, one for the energy and one for the salt. And what's lovely about that is that subject to zero flux boundary conditions, our entropy increases throughout the domain. Okay. So choosing some basic assumptions about the mobility of the system, we get this coupled system for the phase parameter, the internal energy, and the salt. And I'm going to go back to what am I doing here? And in what sense? So I need you to stop looking at my equations. Again, these are just letters and stuff, right? But we need to understand. So again, what do? We have this brine inclusion inside this box of ice, and I'm freezing it. So I'm pushing the salt inside, right? The ice reject the salt. So the salt is moving inside the liquid, but the liquid already has very high salinity in it, right? This is a chemotaxis process.
5 minutes now.
Sorry. Oh, perfect. And I thought I'm perfect. This is a chemotaxis process. And that's exactly what we see here. So in 1970, Keller and Segal introduced a model to describe this type of chemotaxis models. It's very similar to what we have here. So they have this sensitivity function, which we have here, and they have this coupling system of U and V, which couples, in our case, the phase parameter and the salt. Their model became widely used, especially because it was relatively tractable and it drove some nice pattern formation, like traveling wave and pulse going through populations. However, they had some problems. They had no maximum principle, which means that they had to work harder on getting estimates to control the system. And we have the same problem, only we also have strong singularity because of the ice. Let me run through my analysis. Okay, so I'm going to change coordinates again, and that's just to simple the analysis. So I'm not doing anything fancy now. I'm introducing rho, which is the salt density relative to liquid water density. Then I'm expressing the salt as a function of rho and the phase parameter. The key point about this change is that now I can write my potential as a double well, equal depth double well potential plus a small perturbation. So I'm recasting my system. And again, you just need to know that I'm going to look at the phase parameter, the temperature, vector temperature, and the salt. Okay. So adopting a classic sharp interface scaling, multi-scale analysis reduces the problem to a Stefan problem. And what we have zero salt in the ice, and we have a jump in the ice because we have high salinity inside, right? So we have this jump, and this jump means that we have a free parameter. We need to impose one more conditions. We're going to impose a local conservation of salt condition, and then get this boundary condition. And we call it the swooping interfacial boundary condition because the ice comes and it basically sweeps, sweeps the ice into, it sweeps the salt into the liquid region. Okay. Using flux matching, we can show that the normal velocity is coupled to the boundary conditions, and the normal velocity, that's basically a curvature driven flow mediated by the cryoscopic term. Okay. The temperature and the salt will equilibrate on a very fast time scale, while the interface will move on a very slow time scale. So we can talk about the quasi-equilibria. Let's assume that the salt and the temperature equilibrate, and then we want to look at the evolution of the interface. And again, the interface timelines, we're talking about 2 weeks, like something very fast for the salt and the temperature, but several weeks for the interface. I'll just do one quick picture. If I take a vertically oriented axisymmetric reduction of the curvature, then I can express the curvature as the distance from the central line. And the entire problem reduced to a second order ODE, which at this point, I'm always happy. I tell my students that all you need to hear is an ODE because that's what we know how to solve. Given boundary conditions, we can solve it. So I can look, if you look at the dashed line, that's for low temperature gradient. That's taper a little bit. The dotted line tapered more and starts to oscillate. And the solid line for large temperature gradient will already pinch off. Now, these states are most likely dynamically unstable. So I'm not thinking that any of these states will occur. However, it does show us that subject to large temperature gradient, we should expect to find more pinching of the interfaces. Okay. And I'll stop here because I'm done.
Thank you very much.
Thank you.
Thank you. Okay, we have time for one quick question, please. Pat?
Yep. Thank you very much for your talk. It's really informative. From this last picture, but normally from the field, the Brine channel it look a bit like diadentic, like tree-like. So what drives that kind of diagonal movement of Brine channel to join together from your theory?
From my theory?
Yeah. Can we connect with that when it start to form like a tree, like diadentic?
No,
Yeah.
so again, I'm modeling single brine inclusions. Once they start pinching off and breaking into several or merging and connecting into one, my theory doesn't work. So I can't answer that.
Okay, thank you. Yep.
Okay, thank you very much again, Noah.